There we go. All right, I'm just videotaping this class for people that aren't able to make it today. Sorry. And I'm going to put it on Angel just in case you miss anything. You could look at the video as well. But I wanted to start out with questions on the two websites that we're doing today. Anthony?
So the last question on the second website, I didn't have a graphing calculator, so I wasn't really able to do it.
Okay, last question, second website.
It was like use a graphing utility to
oh, maybe the first one you mean? Or do you mean the 3-3 one?
No, it was.
It was?
Yeah, but it's not. That's not what it said. It said using graphing utility to find it.
Oh, this one?
Like in the video, it said using graphing utility.
All right, well, let's look at this problem anyway, because I'm not assuming anybody has a graphing calculator, but what would you do to find the absolute extrema for this one, number 5?
Yeah, I'll show you.
Find the derivative,
I'll bring it up.
find the critical values, and then plug the critical values and the endpoints into the function. So for this problem, when you take the derivative, you get x to the negative 1/2 minus 3. And then to find the critical values, there's 2 ways to do it, but the way that I'm recommending is factor out x to the negative 1/2 and be left with what? What are you left with if you take x to the negative 1/2 out of this term? 1. And out of this term? 3. No. You got to divide. I'm sorry, subtract. You divided 0 minus negative 1/2. 1/2. Right? If you factor out an x to the negative 1/2 when there were no x's, you'll get x to the positive 1/2. Because if you distribute back, negative 1/2 plus positive 1/2 leaves you no x's. So that's the idea. So you have your derivative is 1 minus 3 square root of x over the square root of x. That's what you want to be able to come to, a nice simple version of the derivative. What are your critical numbers then? The numbers that make, let's start with this undefined. What would make this undefined? 0. If you put a 0 in, your denominator would be 0. What would make the numerator 0? What value would I have to put in to make the numerator 0? 1/3 squared, right. So if you make that 0, that means 1 had to equal 3 square root of x. If you move this to the other side, it means 1/3 had to equal the square root of x. It means x must have been a 9th. So that's your other critical value. So the challenge in this section is your algebra skills. You know, that you can set the numerator equal to 0. The good news is the steps are always the same. You do this, and then this, and then this, and then that. The bad news is you have to be able to handle the algebra along the way. So now I want to plug in 0 into my original function, 1/9 into my original function, and what else? What's the third thing I need to plug in? 6, right. 0 because it was an endpoint, and because it was a critical value. It was both. 1/9 because it's a critical value, 6 because it's an endpoint.
So if there was another critical value that wasn't 0, so it's like 1, you plug it in.
All 4. Any endpoints, any critical values. You're plugging into that function right there, the original. And so when you plug 0 in, you get 5. When you plug a ninth in, you get 2/3 minus 1/3 plus 5, so 5 1/3. And when you plug 6 in, you get 2 square root of 6 minus 18. Well, this is the smallest value. So that's your absolute min. And this is the largest, so that's your absolute max. If you have a graphing calculator, you can graph it and you can check yourself. You know, does it look like it maxed out there and then it minned out there? But if you don't, it's not a problem. You're just following the steps.
So then what's the 0, 5? Is that just like a hole in the graph or something?
No, it's a point on the graph, but it just doesn't happen to be your max because it went up higher and then it went down lower. So, you know, the max is here and the min is here.
I see.
So you're just comparing function values to get the greatest and the least. So the biggest thing is knowing the steps, because if you make a little mistake along the way and you get the wrong critical value and you plug it in wrong, but you did all the steps, that's minor. But if you don't know what it means to find an absolute min or max, that's major. So step through it and show me your work and you can get most of the points even if you make a mistake somewhere. Okay, were there any other questions on, well, let's stick with that one. Any other ones on that one? And then, yeah.
That one right above it, 4.
4? Okay. So the quantity demanded is inversely proportional to the cube of the price. That should sound pretty familiar now. The writing a demand function that's inversely proportional. So we've got x equals k over p cubed. Because it says cube of the price, I want a p cubed. When the price is 10, so p cubed is 1,000, the quantity demanded is 125. That helps me figure out what k is, 125,000. So now I know what the demand function is. X equals 125,000 over p cubed. But I'm supposed to maximize profit. How do I get from there to profit? What are the steps that I have to follow to get to profit? Yeah, that's right, Michelle, I saw you do that. Right, p cubed equals 125 over x. So switch your p and your x. Cube root both sides to get p by itself. And so this is going to be 50. And this is going to be the cube root of x, but I'm going to write it as x to the 1/3. Okay, so I switched. I got my demand function the way I need it. How do I get revenue?
Wait, does the x in the denominator become a cube root because you have to cube root the x on the bottom too?
Yeah, you got to cube root all of this.
Oh, it's the whole thing. Okay.
Mm-hmm.
Okay.
Okay, so how do I get revenue? Multiply it by x to get revenue. And how do I multiply that by x? What do I get? 50. 2/3. This is divided by, so I can stick my x up there, but then I got to subtract my exponents. So I get 2/3. And then I need profit. So I got to subtract away my cost, which they said was 140, and $2 for every unit. So there's profit. Okay, so that's all chapter 2. writing a profit function from a demand function. So far so good? Okay, so chapter 3, maximize it. So I want to take the derivative. Now it looks an awful lot like the problem we just did. We had a problem just like this. We factored out the x to the negative exponent. So I'm going to factor out the x to the negative 1/3. I'm also going to factor out a 1/3 from here. Because then what's left inside here will be what? Just the 100 that I didn't take out. Now here's the challenge. What's left here? 6 x to the 1/3.
Why is it 6?
Because I took out a third, so I needed to think about this as 6/3, so I can take a third from it. And it didn't have an x, so when I took out the x to the negative 1/3, I have to have an x to the positive 1/3. And that's what's going to help me solve for x, for the critical values. So again, the critical value from this negative exponent is 0. Why doesn't that make sense in this problem? If I'm trying to maximize profit.
P10 equals $0.
Yeah, well, I didn't make anything, so actually I lost $140. I can't maximize profit if I don't make anything and then I pay $140 to go into business. So I'm just going to throw that one out. But I could get one from here, but that might be my maximum. So I'm going to set 100 equal to 6x to the 1/3 to set that equal to 0. Divide by 6. And then do what? Cube both sides. And whatever that value is my critical value. Now, how do I prove if I found a maximum or not there? Because that's a big part of this quiz. You don't just get the critical value and say, oh, I got a maximum. How do I prove that that's going to maximize my profit? What's the punchline? Because this isn't an absolute. This is a relative max. Yeah, you got to go to intervals here. If I didn't make anything, and then I made all the way up to this, and I'm not calculating it out right now, just to be shortcut about it. And then I went from there on out to infinity. What am I hoping is going to happen so that I can prove I have a maximum? What do I need to happen to show, okay, I just maxed out my graph. My graph just went like this. And I hit the top.
All the other points are lower.
Either all the other points are lower, or even faster.
One side's increasing, the other side's decreasing.
Yeah, the derivative. The derivative's going to help me figure it out. If the derivative's positive on the left, and then it's negative, I maxed out. So all I got to do is look at this and see if I plug in a number like 1, this factor is 94. It's positive. This is positive. This is positive. My whole derivative is positive. My function is increasing. But as soon as I get beyond what makes this 0, so I use a number like 1,000,000. I mean, I can use any number in that interval, but just to make a point, 1,000,000 is going to make this negative. And a positive times a positive times a negative, all right, my derivative is now negative. I found that balancing point that sends me to a negative derivative. 0 is the balancing point where the derivative is 0. I just found the what that maximizes profit. What's x? X is the number of units that maximizes profit. But I think what they asked me for was the price. So I gotta plug it back in here to get the price. So you can do the whole problem right and then not get the price on WebAssign and get the whole problem wrong. You know that's not gonna happen on a test or a quiz, but that's what happens here. So I gotta plug this back in here to figure it out. And that's why I didn't cube it, because I knew I was gonna cube root it. So it's 50 over 3. That's $3. And so that's pulling together a lot of stuff that you should have known, and the one new thing is get that maximum. And actually, you know, the idea of this interval, we're going to have another way to prove that it's a maximum versus a minimum in just a second. So there'll be a little faster way to finish it off. It's called the second derivative test, but we haven't gone into that yet. All right, anything else with this assignment? This is the second, the absolute minimax. Okay, how about the first one? Are there any other questions on the first one, which is the relative extrema? I think they were mostly polynomials, so the derivatives are pretty easy.
Yeah, I think it was that one.
This one?
It was just like use a graphing utility. and
Oh,
that-
yeah.
and
Well,
I
you
didn't-
know, yeah, you don't have to do that because I'm never going to ask you the graphing part, but what I would want you to be able to do is this part for sure.
Okay.
And to find the relative extrema, I want you to take the derivative, find the critical values, go to intervals, and see if you have any maxes or mins. That's what I'm most interested in being able to do. Okay, so were there any of those derivatives or critical values anybody had trouble with? This one? Okay. So, if you were like desperate and you just didn't know what to do about the derivative, what's one thing you could do? Like if you thought, oh gosh, I don't even know what to do with that derivative, so I'm gonna. You could do this. You could expand this out if you wanted to. But since I'm only getting the first derivative, I'm not in section 3.3 yet. I think that it's just as simple to remember the chain rule and bring your 3 down, drop the degree to 2, and multiply by 1.
So your critical point would be 7, right?
So, and that's the only critical value I have. So all I gotta do is go from negative infinity to 7, and from 7 to infinity. Now when you set up your intervals, you gotta know what the domain of this is. If this had been a square root, like that, the problem would be a lot the same, except I couldn't start at negative infinity. Because I couldn't put that in there. I'd have to start at 7. That's the domain of that radical. So you have to know that. But since the domain was all real numbers, I'm taking the entire number line. And then I'm just going to check what happens when I go to the left and the right of 7. So my derivative, nothing. It's going to get squared. It's going to be positive. I don't have any extrema. This thing never turns around. It doesn't change direction. None. It's because of the sign. This is always greater than or equal to 0. no sign change, they're no extrema. Okay, if this had been a 5, the answer would be the same. 7, a 9. If this had been even, then we'd have a totally different story. Okay, anything else? Does anybody not have that section 3.3 sheet from last time? Was anybody not here last time? We're just going to finish the back of it. And then we're going to look at the review sheet for the quiz. Okay, so the biggest thing to remember, going from section 3.2, 3.1 and 3.2 to section 3.3 is that the first derivative tells you about the direction of your graph. Is it rising? Is it falling? But now we're jumping to section 3.3 where we said the second derivative tells us about the concavity of it. Is it concave up, meaning it'll hold water, or concave down? That the water would fall out. So that's what the second derivative tells us. And that's what we talked about last time, the picture of it. A function can be increasing, but concave up. It could also be increasing and concave down. The concavity doesn't have anything to do with whether it's increasing or decreasing. So they're separate from each other. And then we talked about these two examples. We took the second derivative and looked and saw what happened. Well, now we're going to look at another use for the second derivative on the back. And it's this thing called the second derivative test. Because the second derivative tells you about concavity, if you have a critical value and you plug it into the second derivative, it'll tell you whether it's a min or a max right away, as long as it comes out positive or negative. If the second derivative comes out 0, it doesn't tell you anything. But if you have the second derivative and your critical value makes it positive, then it means you had a minimum. And if the critical value makes it negative, you had a maximum. So it's a real shortcut for relative extrema. I don't have to use intervals and see what happens to my curve. I can just use this second derivative test. It fails, though, if the second derivative is undefined or 0. It won't help me at all. But let's look at this example. You probably already know the shape of this, or you should know that the shape of it is something like this. But let's go and find, we're trying to find the maxes and mins of this. So let's find the first derivative. And then figure out the critical values. So critical values are 0 and 1. Right. If you factor out a 6x, you can see that x equals 0 and x equals 1 make that 0. Nothing make it undefined, so those are my two critical values. So if I want to see if these are maxes or mins, one thing I could do is go to the number line and write my intervals and check the sign. But the second derivative test says another thing I could do is take the second derivative. So that's 12x minus 6. And then just plug in my 0 and my 1. So when x equals 0, y prime prime equals 12 times 0 minus 6. It's negative. My function right there is concave down. So I know that 0, and when I plug 0 back into my function, I get 8 out. 0, 8 is a what? Max or min? Yeah, because it was concave down there, it had to be a max. It couldn't have been a min. So that's a relative max. So this is an alternative to showing that the graph went from increasing to decreasing. You just find the value of the second derivative. It's optional. You don't have to use it, but it's a possible way to make things a little bit faster. Because when you put 1 into the second derivative and you get a positive value, and you say your graph was then concave up, you could say 1, 7, when I plug 1 into the function I get 7 out, is a relative min. So the second derivative just helps me categorize these critical values that I got.
Where'd you get the 8 and the 7 from?
I plugged the 0 back into the original function to get 8, and then I plugged the 1. Because see, this original function is going to give me the y value when I give it an x value. And a relative max or min is a point, an x matched with a y. So I need to go back to the original function to get that y value. So we could add this to this if you want to. The original function, when you plug x values in, tells you the y value. The derivative, when you plug x values in, tells you the direction. And the second derivative, when you plug x values in, tells you the concavity. Okay, that's their use in these problems. And then finally, we talked briefly about when concavity changes, you get these points here that are called inflection points. So we touched on that last time. If you find a place where the concavity changes from either concave up to down or vice versa, you know, an inflection point could happen like this, too, where concavity changes from down to up. But in economics, the most common application of this is called the point of diminishing returns. How many people have seen those words before in an economics class? Okay. So you have a general idea that diminishing returns means after this point, every dollar that I put in is going to give me not quite as much back. So I don't get quite as much bang for my buck for every dollar I spend. So let's pretend that this was my profit function. Okay, and I decide this is when I sold 10,000 units. Well, if I sell 10,001 units, I'm going to make more profit. This function is rising. I can continue to make profit. However, at this point, I'm making profit at the greatest rate I can because the tangent has gone vertical. So the rate of change in profit is as big as it can be. And so if I keep spending money, every dollar I spend, I'm just going to get a little less back. And so some people want to stop at this point in diminishing returns. Even though I can get more money, it's just not going to be worth it for me. So it's often the point that producers are looking for. And not necessarily spending 10,000, but what price I should set to spend to sell 10,000. So in order to find that point of diminishing returns, all I got to do is find where the concavity changes, which means it's all about the second derivative. So here's an example. I'm spending this much money on advertising, and it yields this much sales. And I'm trying to figure out, when should I stop putting money into advertising? When do I hit that point of diminishing returns? So I've got to go from the first derivative immediately to the second derivative, because the first derivative is not going to tell me about concavity. So I'll take the first, but only because I need the second. And I'm saying that because a lot of people on my quiz set the first derivative equal to 0 for point of diminishing returns. Okay, so you don't want to do that. You want to set the second derivative equal to 0. Okay, and that's where I'm going to get my critical values. So step 1, get the second derivative. Step 2, get the critical number, or numbers. And that's when 3/5 x is equal to 12, or when x is equal to 20, if you multiply both sides by 5/3. Okay, so now what do I do? What do you think step 3 is? Second derivative.
First derivative.
No, nothing to do with the first derivative.
Put it in the original.
If I plug it into the original, I'll get the amount of sales, yeah. But how do I know if this is a point of diminishing returns? Just because it made the second derivative 0 doesn't mean it's a point of diminishing returns. It's just a critical number. Prove to me that it's a point of diminishing returns. If I plug it into the second derivative, I'm going to get 0, right? That's how I found it. But it does have to do with the second derivative. Anybody else? Think about section 3.2. Do what?
Set it equal to 20.
21, did you say? No.
Like negative 3/5 x plus 12 equals 20.
Oh, no. No, I don't want to set it equal to 20. No, but that's a good, I see what you're saying. 20 is this value that I think might be the point of diminishing returns. How do I know if it is? What should happen if it is? If it's this magical point where concavity goes from up to down, what should happen?
Everything to the right is positive.
Everything what to the right?
Everything bigger than 20 is positive.
Not pod, no.
Say x equals 0.
But you're getting there. Everything bigger than 20.
And then everything less than 20.
Everything less than 20.
And then you,
But what should happen to the left of 20 if I want this?
You want it in.
What am I going to check to see if I have this?
No way.
concavity.
Concavity, right? I need to check concavity. So I need the second derivative. And do I want it to be positive or negative? No. Positive second
Negative.
derivative means concave up. Negative second derivative means concave down. Positive first derivative means increase. Negative means decrease. Okay? So I want to see if my second derivative is always positive to the left. So I'm going to put a number like 0 in to my second derivative, and I'm going to get 12. That's positive. So good. So far, so good. My function was concave up. Then I get beyond 20. So I'll put in like 100. This will be negative 60. And I'll add 12, and I'm negative. Bingo. I just proved that concavity changed when x was 20. I found the point of diminishing returns. Now I'll plug it back in to the original function to get the y value.
Wait, but did you plug in the 100 into the derivative 1 or 2?
second derivative. Once I get the first derivative, I don't want it anymore. It doesn't tell me about concavity. It just helped me get the second derivative. So this is what you got to grab a hold of for this. If I want to know about concavity, then I want the second derivative. That's what I'm going to plug into. If I want inflection points, or I want the point of diminishing returns, it's all about the second derivative. If I want max and min, it's all about the first derivative. But in the end, I'm always going to plug it into the y to get the second part of my ordered pair. So I'm going to plug it in here and get negative 8,000 over 10 plus 6 times 40 plus 400, whatever that is. That's my y value. Okay, so inflection points, you do this exactly what you did in 3-2, but you do it with the second derivative. And actually, that's usually easier because the second derivative is usually easier than the first, especially when it's a polynomial. Okay, so that's section 3.3. That's what your web assigns on. And we're going to have time on Monday to go over it. We also have a couple minutes now to go over questions on the review, which I know some people have already done. So I'm going to hand it out just in case. Did anybody need it? Rick, okay. Do you have it? Yeah.
The review?
The review sheet
For what?
for the quiz.
What's that?
Monday.
Oh, the Schultz.
I knew I shouldn't have given you flex time on that homework because everybody took it. Not everybody. All right. So John, did you have a specific question on this?
Yeah.
Just on number 6, and could we go over the steps of finding absolute extreme again?
Sure. Yeah, so what I did, the answers to this are an angel. Worked out pretty, and with a lot of steps. But for absolute, let's just quickly go through increasing and decreasing. The steps would be find the derivative, find the critical values, set up intervals, and check the sign of f prime. So that was section 3.1. That's where we started this whole thing. We took the derivative, found the critical numbers, put the intervals and said, okay, derivative is positive, it's increasing. Derivative is negative, it's decreasing. That kind of thing. Number 2 is exactly the same as number 1, except what else do you have to do?
Oh, you did the original.
Yeah, you need to get the y value and call it max or min. So max if the direction went from increasing to decreasing, and min if it went the other way. So it's almost exactly the same as number 1. It's just that you have to actually label these things that you found, the change in direction. But your question was, what about absolute extrema? How is that different? Well, if you remember, we said you first find the derivative, and then you find the critical values. But that's where it changes. Okay, those first 2 steps are going to be the same. But after that, for absolute, you're going to plug the critical numbers and the endpoints into what? No.
The original problem.
Yeah. Because that's how we started class today with that absolute question. We plugged them all into the original function and we compared these y values. And the biggest was the max and the smallest was the min. So once you get the critical values on absolute, it doesn't have anything to do with the derivative. You're not looking for turnaround. You're just looking for biggest and smallest. Absolute. Awesome.
If your critical point doesn't fall in between your endpoints, you don't have to plug it in.
Yes, and that's a good point. Yeah, so find and plug the critical numbers that are in the interval. I should have said that. Thank you for. Because if your critical numbers are outside of 3 to 5, they're not going to be extrema on that interval, right?
So then what do you do with them? You just kind of ignore them?
Yeah, they can't be your answer. Yeah, so. Okay, so that's the steps for that. Point of inflection, you're going to do the exact same thing as number 2, but with the second derivative. So you're going to take the second derivative. You're going to find the critical values from the second derivative. You're going to set up intervals. You're going to check the sign, but it's all with the second derivative, not the first. You're looking for change in direction, but it's change in direction with concavity, not increasing, decreasing. Okay, so that's going to flow down to this, but it's got to go from up to down to be a point of diminishing returns. Point of diminishing returns is an inflection point, but it's an inflection point that only goes up to down, not the other way. So if it doesn't go positive and then negative, it's not a point of diminishing returns. It's just an inflection. So this is section 3.3. Okay, so those are where you want to focus most of your time and energy is, can I find the derivative? Do I know how to set it equal to 0? And then where to go?
So this quiz is just going to be on this stuff here.
Yeah, now there's going to be an extra credit on the quiz that's like number 6. So I did want to go over that. We've seen this before. I've put this on things before. But now you really should have a firm grasp of these 3 things, right? That if I tell you about f of a number, I'm telling you a y value. So what does that first line tell you? What should I do from that first line? No, it doesn't. It's not f prime. It's not the slope. It's that f of 0 is 0. What does that mean? Yeah, it's a point.
0,
0,
0.
0. 0, 0 is a point on the graph. When I plug in 2, I get out 0. That's another point on the graph. So if I'm telling you about f, I'm just giving you points that you should put on the graph. So I need, when x is 0, y is 0. When x is 2, y is 0. They have to be on my graph. Now I'm telling you about the first derivative, which means I'm telling you direction of your graph. So if you put in values that are less than 1, your graph should be increasing or decreasing?
Increasing.
Increasing, yeah. So whenever you're less than this number here, when x is 1, your graph is increasing. So I could just make my graph go up. And then I'll skip down to here, which is the matching kind of statement.